All right, so let me introduce to you Zeng, who is a professor at the University of Irvine, also the lab director. He's going to talk with us today about tinnitus perception and treatment. He is a good friend of the House Institute, and very honored to have him here today. So Feng, thank you very much for joining us.
All right, thank you, Laura, thank you, Bill. And so Bill didn't say that I used to work at a house, right? And I was there from 1990 to 1998. So I was there for 8 years.
We'll always claim you.
Absolutely. All right, yeah, so I'll just talk about two things today. One, about the tinnitus perception. The other is how do we treat it or get rid of it if we can. And you can interrupt me at any time, ask questions, make this more dialogue. I just invested in several companies, so that's my conflict of interest. And the work I'm going to talk to you about has been supported by NIH. Well, I'll say a few words about UCI, especially our Center for Hearing Research. And Irvine is a relatively young school, and we're actually the third youngest among 10 UC campuses. And we have about 35 undergrads and 6,000 graduate students. And we're keep going up or moving up in terms of ranking. So we're right now the number 8th best public universities in the United States. And in terms of the center I'm running, we have about 40 faculty members from 5 different local universities and 10 different departments. And they do everything from molecular biology to artificial intelligence. And we have a lot of research projects going on, and we have a core grant, and we have a training grant to support our students and the postdocs. And we also have a very active advisory board. So that's my little advertisement for my institute. Let's talk about the tinnitus. And most of you know that tinnitus is actually very prevalent, affecting about 15% of the general population. And a fraction of those who actually feel their tinnitus affect their life so much that they actually go see you guys or me. And it's has been number 1 disability among veterans, all the way from Korea War to the most recent Afghan and Iraq wars. And also, you think it's a comorbid condition with aging, get old, people get tinnitus, and also 80% overlap with the hearing loss. And recently, a lot more people have both tinnitus and sensitivity to sound. We call it hyperacusis. And those conditions, they make you fatigue, lose your concentration, stressed, depressed, and some of them may even thinking about committing suicide. If you go to Reddit, I don't know how many of you guys actually go to Reddit. What I notice is a lot of young guys these days, they don't have hearing loss, normal audiogram. They complain a lot about the tinnitus. And I wonder what happened to these guys, probably overexposure to noise, too much usage of iPhones, iPad, or whatever other things. And right now, we really don't know what causes tinnitus. There's a lot of theories, right? And quite a few myths. And one of them, and if any of you guys doing animal research, and sometimes you wonder, how do you know an animal has tinnitus? And it would be nice to have an animal model so you can study the neural mechanisms, right? Open up the head, poke electrodes inside, and you can record and see what happens. But how do you know? a rat, guinea pig, a cat has tinnitus, right? It's very difficult. And one of the animal models people have used is the so-called filling in the temporal gap, right? And I'll tell you, what that means. The other myth, I think most of you guys, or including myself, working directly with the patients, is that they will say, "Oh yeah, my tinnitus. They make me hear sounds, giving me a great degree of difficulty in listening, especially speech and noise." Right? You go read all even the scientific papers. That's what people say. And what I'm going to tell you, the first part is none of them is true. Right? None of them is true. Let's first take down the first myth. Does tinnitus really fill in the gap? Now, what does a gap mean? What I'm showing you here is just like a sound, a waveform intensity as a function of the time. In this case, maybe a noise, right? You hear noise versus another noise, you don't hear any, right? And your job is to say, hey, whether there's a gap or not. And the idea using this paradigm to study or to develop a tinnitus animal model is that if an animal can hear a gap, right, like right, and then if it's loud enough, and then the animal will just like startled, and you just, hey, a loud sound, or maybe, from millions of evolution, the rat may thought, hey, there's some cat trying to catch me, right? So you have a startle response. And the idea is, if you have a tinnitus, right, the tinnitus will cover up the gap, so will reduce or even eliminate this startle response, which you can record objectively, right, in animals. And this is a animal or filling in gap model, tinnitus animal model, by a group of researchers at the University of Northern Illinois. That was about 2006, 15 years ago, and has been widely used, right, in animal research. And people first accepted the fact, yeah, probably, yeah, that sounds pretty cool. Just using this tinnitus filling in the temporal gap and use that as animal model to study neural mechanisms. This is true. So a number of people have tried to see whether tinnitus patients, human beings, humans with the tinnitus, actually have a deficit in detecting temporal gap compared with the normal control, those who don't have any tinnitus. And one of the studies they did was they introduced a temporal gap, but the temporal gap, the problem is the gap intensity is so high that the tinnitus loudness might be much lower relative to your external gap, such that you can still hear the temporal gap very well. And of course, under this condition, well, you don't see any deficit in gap detection by tinnitus patients. Right? And other people did a study where they may use, say, the tinnitus is typically high pitched. Most of, some of you guys may have it. Usually it's like this kind of high pitched sound, right? Represented by this red line here. But if you use a low frequency external sounds to represent that gap, like a boo boo, right? Of course, there's no overlap in their frequency components, and you can detect the gap just focusing on the low frequency channels. Ignore your tinnitus, right? And so the previous studies, 3 or 4 I mentioned, they said, okay, yeah, somehow patients with the tinnitus did not seem to have any problem detecting temporal gap, but because of the either mismatch in intensity or in frequency, right? So it's not really conclusive. So that's where what we did. So what do we say? What if we match the external sound, right? And that BB, we make sure they're equally loud as their tinnitus, and they have the same pitch as their tinnitus, like this. Now, this is really challenging, right? And if the tinnitus fill in the temporal gap, and under this controlled or matched condition, our prediction would be that tinnitus patients would have a tremendous difficulty in detecting temporal gap, right? Compared with the normal controls. Well, let's find out whether that's true or not. And this study was published just last year, and the work was done by a couple of graduate students, Matt Richardson and Katie Turner. So we first just get 10 normal controls, young kids, no hearing loss, no tinnitus, and we present the tones at a very low level, 10 dB SL, measure their threshold. And in this case, what we did? We did 3 conditions, 500 Hertz, 2000 Hertz, and 8000 Hertz, try to cover the whole range, right? And then we presented them at a 10 dB SL, and you will see why we presented such low level, because they're matched to the patient's tinnitus. And roughly, it will require about 20 milliseconds for this young control group without hearing loss, without tinnitus, to hear there's a gap. So that's our gold standard. So we just grab a group of tinnitus subjects. They're a little bit older. They have maybe tinnitus. Some of them may have a little bit high frequency hearing loss, which is typical. But in this case, we control the degree of hearing loss by matching, right, the sound at the 3 frequencies, right? Also presented 10 dB sensation level. If you look at the control and the triangle tinnitus data, no difference in their ability to detect the gap, right? So at least in this case, the 3 pitches, 3 different frequencies from low to high, present them at low levels, whatever the tinnitus in this in their head did not interfere their ability to detect a gap. The third condition we did, not only did we match the loudness, remember some people may have a lower, their tinnitus may be lower frequency, other may be higher frequency. We individually match the pitch to each one of them and then measure what their gap detection threshold, and that's the individual data. And that's more than 11 because 2 or 3 subjects, they have a multiple tinnitus pitches. So we did it in 2 or 3 conditions in the same subject. If you get the grand average, right there, fall in what you would expect from that young, normal hearing, no tinnitus control group. So even we perfectly match the tinnitus on individual basis, we didn't find any difference between the gold standard and this tinnitus group. In other words, tinnitus, the inside sound in the head, did not interfere with the gap detection, and many other experiments we did, tasks we did not interfere with the perception of the external sounds. That's a major discovery. That is very counterintuitive, right? And I'll tell you, why. And then maybe I'll stop here for a quick second, see if you guys have any questions. Any questions so far?
This is good. Let me ask our fellows if for a question. One of them needs to come forward.
Okay, so no answer means that's no question, right?
Let me ask you this: these are normal controls that did not have tinnitus, correct?
No, they did not. That's correct.
Yeah.
No, that's a key point. Otherwise, the whole thing wouldn't hold.
Yeah.
All right. So the next question, remember we said, hey, does tinnitus really interfere with the speech perception in noise, right? And we picked a paradigm which we previously established, right? We say, hey, let's present a speech, and the speech in this case is a male voice speaking like daily sentences. We call IEEE sentences. And then we have three types of backgrounds. They're either steady state noise whose spectrum was matched to that male talker's long-term spectrum, or another two conditions where we have introduced a female talker. And of course, the task was, hey, don't ignore the female talker, pay attention and see how much you can understand the male talker. And the third one is a little more difficult, a different male talker as a background, right? And then we just adjust the relative level, we call the signal to noise ratio, so that we say, well, what's roughly signal ratio do you need so you get a 50% intelligibility, understand half of the sentences, right? And this is a measure that widely used to see very, very sensitive, right? To see whether you have any difficulty in understanding speech in noise. Well, here's the results. The y-axis showing you, we call it at a signal noise ratio that you require to detect 50% speech recognition. The lower, the better. So that's why minus 25 on top, right? And the x-axis is the three conditions. And the field black bar is the control. The same, young, normal hearing, no tinnitus, gold standard. And this is 31 tinnitus subjects. The blue open bars, it's no difference. Whether it's a steady state noise or two different people speaking at the same time, being either female or different male talker, there's no difference. Right? So that's another myth that a debunker. Even under this very controlled and sensitive measure conditions, there's no difference between our young normal control and our tinnitus subjects. So whatever the problem, your tinnitus subjects complaining about understanding speech noise was more likely related to their degree of hearing loss, not their tinnitus per se. Okay, all right. So what do we think? Do we make out of these, right? And so here's what we think might happen. The tinnitus is generated from the inside as some kind of a neuron noise, and they comes in, from the top. The sound, speech, tones, or whatever environmental sounds you hear goes from the ear and goes to the brain. It's a bottom up. They travel through different pathways. They don't physically interact with each other. They can only interact with each other through attention mechanism. So we develop a model, trying to use this model to explain what we found. If you're interested, read this paper. To a large extent, this model, I think, can not only explain the data we produced, but also some of the things that we scratch our head, we don't have an answer. I'll just tell you what it is. Say, if you work with a tinnitus patient, you ask the guy or the person says, how loud is your tinnitus? They will say, wow, it's so loud, just 7 out of 10, just drive me crazy. I cannot sleep, I cannot do this, I cannot do that. And then say, okay, would you please try to match your tinnitus to this external sound? Very often, the external sound that matched is typical as you see, 10 dB or 15 dB above the threshold, which is not very loud if you just hear that sound by itself. So there's a huge discrepancy between their subjective perception of loudness and the objective match to external sound. And for a long time, I've been in this field for a while. I don't know why, what happened? How do you explain that discrepancy? Well, and now by doing this study and using this model, an attention model can explain it. The idea is when there's no sound, especially when you try to sleep, sitting in a quiet room, all your attention focuses on your tinnitus. It's so loud, right? By the time you ask the person to match the internal tinnitus to external sound, you switch the attention from internal sound, tinnitus, to the external sound. And therefore, the loudness of tinnitus is reduced as a process of that matching, right? That's how we explain that discrepancy. I hope that that's clear. Okay, so far, so good. So this, I'll just conclude the first part of my talk. It's about tinnitus perception. If anybody still trying to tell you tinnitus fills in a temporal gap, well, it does not. Tinnitus is not physical sound. It does not fill in a physical sounds gap, right? Does tinnitus impair speech perception? No, not by itself, but because remember, tinnitus also associated with hearing loss, hyperacusis, and other cognitive issues, right? It's the other problems, not the tinnitus itself. They impair speech perception. So that's the second conclusion. And the third, that's still my working hypothesis. I wouldn't say it's a still theory. I think tinnitus is a result of increased central noise, some kind of neural noise in your brain. But that can be modulated by attention. Okay, so that's a kind of the take-home message. Take-home messages for you guys. Any questions now?
I have a question. Sorry, go ahead, Dr. Beckman.
This is Daryl Fang-Yang. Enjoy your talk.
Hey, Daryl, how are you doing?
I'm doing well, thank you. In industrial ratings for impairment, if they have tinnitus, they say tinnitus without impairment is not rateable. But if you have hearing impairment and tinnitus, you can add up to 5% impairment for the tinnitus, because the theory is that it interferes with speech, and tinnitus interferes with speech understanding. But that, what you've said, that doesn't jive, doesn't it? That's not really true.
No, that's exactly what I said. It's not true. When I did this experiment, we made sure the sound was presented at the same level, whether you have hearing loss or not. So you have to exclude a lot of other factors. And under those conditions, tinnitus does not impair or interfere with speech perception. And in most cases, that's very difficult to do. Did I answer your question, Dr. Brackman?
Yeah, I did, Fang-Yang. I don't. It's not going to change anything. But that's giving them the benefit of the doubt that it actually interferes when it really probably doesn't. So that's interesting. But like I say, it's not going to change anything probably.
Yeah, it will not change anything, but it may impact reimbursement and also compensation. And that's we don't know yet. We don't know yet. But I think this is the first time we actually have a solid evidence. I didn't say we did like I think 40 or so behavior tests, and 36 of those measures, there's no difference. Another three showed actually slight improvement by tinnitus subjects, and one showed worse. Okay, I think there's another question. I didn't get it. Would you please ask?
Hi, Dr. Zeng. This is Hossein, one of the fellows. Great talk
Hey,
so far.
good to hear you.
Good to see you as well. I had a question about the last kind of bullet point. What is the implication of this for sort of, taking the route of peripheral treatment for tinnitus, such as, sound therapy or the electrical stimulation that you've been working on?
Okay, thank you for asking this question, Hossein. Let's go. This is the second part of my question. I think it has a great implication in terms of the treatment. Right. Well, Hossein, as well as I do, there's no treatment for tinnitus right now. There is no treatment for tinnitus right now. So all the things you see, you Google on the internet, right? I just said, this is something I just Googled. Tinnitus treatment, that's what you have. And this is all I call snake oil, right? And that's why nobody reimburses tinnitus treatment, except there's one, CBT, cognitive behavior therapy. I don't know whether it's reimbursed by Medicare yet, but in Europe, yes. Right? But it didn't get rid of tinnitus, right? It reduces symptom. Basically, the idea is just let it go, right? Since there's no way you can get rid of it, no treatment, why bother? Don't think about it. And it's a kind of a mindfulness kind of approach to this problem. And I think it's still useful to help people. But I'll tell you, I didn't have any tinnitus 10 years ago. I do now, starting with my left ear and now going to my right ear, and the tinnitus getting louder and they last longer. Do I wish I don't have it? Of course, I wish I can make it go away, right? So I think a CBT, attention-related mechanism, has its own role in helping you better cope with tinnitus, but does not address the root cause of tinnitus. Where does it come from? I said that we don't know, but I know I didn't have it before. I do now. It has to come from somewhere, and I'll present some hypotheses and some potential treatment for you. And again, when it comes to treatment, right? All of you guys, you'll see so many tinnitus patients. Now and over your career. For a long time, right, people thought, hey, let's use white noise. And I think Jack Vernon had something to do with this, and he's a guy who proposed this and advocated for the use of a white noise as a sound therapy to suppress tinnitus. And this is a study I don't have the time to talk about, and you can read the paper we published in 2012 in Journal of Association for Research in Otolaryngology, JARO. It turns out that's not true at all. The best sound to suppress tinnitus is actually dynamic sound. It's not that steady white noise. Shh. It's a sound that has modulation components, like changes in frequency or changes in loudness. We call them amplitude modulated or frequency modulated sound. And the trick is that carrier frequency has to be matched to tinnitus pitch. And we demonstrated it's at least 4 or 5 times more effective than white noise, presented the same level in suppressing individuals' tinnitus. And that study Actually, Dr. Slattery was one of the 3 centers did a clinical trial using this technology. And recently, the 2 European groups and also replicated in our results. So I think the sound therapy still is effective. And what we learned from this is works for very well for about a third of those populations. Another third to some degree, another third really didn't work at all. And we ask why. Well, I think a big why is the following. Electric stimulation will be the key to it. And I'll start with a kind of historical paper. I don't know whether Dr. John House is here, but I would like to pay a tribute to both Dr. John House and Dr. William House. And if you see this 1984 paper by Dr. John House talking about effects of electric stimulation on tinnitus, and the 2 highlighted sentences, our early experience with the use of cochlear implants indicated that chronic electric stimulation to inner ear tends to help tinnitus. And he quoted a William House 1982 paper I couldn't find and was not listed in the back of the reference. Maybe Dr. Bragman can help me find that paper. I think that's one of the earliest papers showing the effectiveness of cochlear implants on tinnitus, right? So we know cochlear implants. Go ahead.
No, I don't. I don't know. You say this paper that you're showing, Fang Gang. Well, no, you see that's published in the Journal of Laryngology and Neurotology. So, which one that can't you find, Fang Gang?
It's the one quoted 1982. William House. Can you see this part? William House, 1982, recently reported that about.
Yeah, I don't know. I don't know where that would where you would find that.
Is it our library or the library at the House Year Institute is still there?
No, the library is actually part of it has been sent over to Good Samaritan, and part of it has been retired. I'll put it that way. That sounds nicer than having it destroyed.
I would have loved to go back and dig it out. You know, that can be historical paper. I think you can see why. Right? So, like Jose also asked, why sometimes sound therapy doesn't work, right? What might happen? This is another leading hypothesis, right, about the origin of tinnitus. And the idea came from Lieberman's paper in 29. When we have inner hair cells, each inner hair cell have about 10 to 15 auditory nerve fibers, okay, attached to it. And some of them, the ones from the lateral side, they have a low threshold and high spontaneous activities. And for those from the medial side, we call them low spontaneous rate fibers, but they have a higher threshold. They're very thin. They're very susceptible to noise. When you have even moderate level noise exposure, as demonstrated by Kojowa and Lieberman, right? The synapses may be gone, and these neurons, high threshold neurons, low spontaneous activity neurons, they will retract or even degenerate. Remember, they have high threshold. When you measure the threshold in these animals or potentially people, they have a normal audiogram. But their input to the brain is greatly reduced because you lose a bunch of high spontaneous fibers, right? And so maybe your brain has to work a lot harder to compensate for it. And sometimes it over amplify. Well, you have a tinnitus. If these neurons, they are detached from the inner hair cells, I don't care what sound you deliver to the ear, it will not activate. It will not activate these detached neurons. Only electric stimulation can activate it. Now, if you go back to the older days, the classical studies done by William House and John House showing cochlear implants are effective in terms of tinnitus suppression. But remember, most of the tinnitus patients showing up in your clinic, they have a little or no hearing loss, right? Do you want to give them a cochlear implant that will likely destroy what they're hearing, the residual hearing or normal hearing? You may cure their tinnitus, but they cannot hear, right? So you cannot really do that. So we needed something in the middle. That is, you want to steer using electric stimulation to suppress tinnitus, but you want to preserve or don't cause any hearing loss. Make sense?
Yes.
Okay, all right. So this is the things that are going on in my lab right now. And so we'll say, how do we stimulate detached auditory nerves without causing hearing loss? And of course, well, let's place 2 electrodes, right? We call it transcranial stimulation, positive on one, and another returning electrode on the other side. And of course, we can place the electrode, in this case, maybe in the ear canal or as close as possible to the cochlea. And hopefully the current will pass through these detached auditory nerve fibers. So we don't damage their hearing, maybe treat their tinnitus. And the worst, if we have to, maybe down the road, we'll develop a cochlear implant that was so thin, so tiny, that we can put them inside the inner ear, but not causing tinnitus. I think it's possible. I think Dr. Brackman would agree. Someday we'll be able to do that. But before we get that kind of cochlear implant, so we tried a whole bunch. This is what I'm showing the tools we have. One of them, we just like your music ear plug, we coated with a layer of gold, so make it conductive. We roll it up, squeeze it inside, so make a nice contact with the eardrum. And we also tried without in this case we call it a wick electrode. It's just like a cotton ball, right? And we can place them on the eardrum or tympanic membrane, and we want to using a couple of holders to make sure they don't move around. So we tried all of these, and we also said this is whatever I showed before, they're non-invasive at all. Or what about the minimum invasive? Because we want to really get inside. And in this case, we place a ball electrode. In this case, we have a couple of surgeons, Dr. Hamid Jalilin and Harrison Lane, and they make a little section to the eardrum and place an electrode inside, either on the promontory or the round window. And it took us a while to find a way to really stabilize the system. And we can just do in the office a minor procedure, and the patient just sit there, and we deliver electric stimulation, and we see whether it's going to work or not. This is ongoing research, and I'll show you the best result we got so far. So what we did, once Hamid put in the electrode, make sure it's on the round window, and we deliver a little tiny electrodes current, and make sure it's not too much. Can you hear it or not? And you have to be very careful. You don't want to overstimulate the patient. So what it showed here is the loudness estimate on the y-axis, and this is the time in minutes. So we introduce at a 0 minute electric stimulation, and that lasts for about 10 minutes. And every half minute, we ask the tinnitus patient, sitting on that comfy chair, how loud is your tinnitus? How loud is that electric sound that you heard? So when we turn it on, and you can see in this case, the electric stimulation, the patient, oh, I hear the sound. It's about 4 loud, indicated by these blue triangles. Just about a half minute, and the patient said, hey, the tinnitus went away, but I can still hear your electric sound. And about 2 minutes, the tinnitus, I mean, the electric sound, the electric stimulation just disappeared. And the tinnitus comes back to 2 a little bit, and they keep that going about 6 minutes into that electric stimulation. The subject said, boy, I couldn't hear neither your electric sound nor my tinnitus. They both seems to have gone away. And at the 10 minutes mark, when we turned that electric stimulation off, tinnitus, there's a residual inhibition, and the tinnitus gone. And we waited for 10 minutes. Has your tinnitus come back? Has your tinnitus come back? No, not yet. An hour? No, not yet. We just say, why don't you go home? Tell us when it comes back. And about 12 or so p.m. at night, and the patient called, yeah, my tinnitus finally came back, but I have a wonderful, 10-hour silence in a long time, for a while, in a long time. Now, what happened during that 10-minute course of electric stimulation on the round window, right? And I'll show you the waveforms, and this is something we monitor. And in the beginning of the electric stimulation, we deliver a biophysical pulse electric stimulation, like all modern cochlear implants. This is voltage, but it's charge balanced. When you see the current, it's a rectangular, it's more like a rectangular current. The voltage, is a little bit deformed, but that's okay. That's what it looks like in the beginning of the electric stimulation on the left. And on the right is the very end of that 10-minute electric stimulation. Identical means there's no change in the physical interface between the electrode and whatever the tissue. So whatever the dynamics or the changes in loudness of either the electric stimulation itself or the tinnitus is reflected probably whatever the brain mechanisms, the changes inside the head, nothing to do with our outside electric stimulation. Right. Okay, to conclude my talk, and I think we're trying to develop a clinic management strategies more in terms of getting rid of, if possible at all, the tinnitus. So we started by asking a question, do you have tinnitus? If you say not much, we'll try the least invasive, the most convenient acoustic stimulation or sound therapy. See whether it's going to work or not, right? If it works, if the person is deaf, let's just go straight to cochlear implant, right? And if the acoustic stimulation works, happy camper, I expect 1/3 of the population will just take home whatever the hearing aid, the iPhone or the sound therapy program. But you have another 2/3 of them that said, no, I want something more, better. Well, maybe we should try the non-invasive electric stimulation. that can be behind the mastoid. I mean, with the active electrode being placed on the mastoid or in the ear canal or tympanic membrane. Will that work? If it works, you're happy. Take it home. Maybe we have like a chronic device for the patient to take home. Whenever tinnitus bothers, you can wear and use it. Maybe another third said, no, I tried sound therapy, doesn't work. This non-invasive stuff doesn't work. Well, maybe we should try a round window, a promontory electric stimulation. I mean, this is not a new idea. I mean, Dr. Slattery probably know. I mean, the French guys did it, and Jay Rubinstein did it. And the problem is we don't have a commercial device, right? If you say, hey, can you give me something that FDA cleared or approved so I can prescribe to my patient? Doesn't cost $10,000. We don't have that thing yet. This is what we're trying to develop. And I expect this a third of these guys will be happy. Maybe a few of them still says, I tried all of this, still doesn't work. And they still have a good hearing. Well, that requires us to develop maybe a mini cochlear implant, which will stimulate, hopefully, these detached neurons without causing any hearing loss. That will be our dream. So we have a full battery of tools, from simple sound therapy devices to cochlear implants that we can give to our patient on an individual basis, help them. And I think that will be, I think my dream, I think it can be done in the next 5 years, maybe 10, depending on how much effort we put in and how much money we can get to support this work. Thank you very much, and I'll answer any questions you may have. These are the people who have worked diligently on this project, and the American Tinnitus Association and NIH supported this work.
Hello, my name is Dr. Kevin Peng, neurotologist here at the House Institute. Thank you for watching this video. The House Institute provides free educational videos for hearing health professionals worldwide. To help support videos like these and other educational efforts, please consider donating by clicking the link in the description box below. Your generous support allows us to keep videos like these at no cost for you and others. Thank you.